there you go.
So academic communities and public sectors have been using mobility. Academic communities and public sectors have been using mobility and traffic data to address social issues such as GDP prediction, environmental impact, and crime, and so forth. And one method to measure mobility and traffic state is by analyzing a series of pictures and footage from traffic cameras installed at the fixed locations. So for this project, our initial motivation was based off the assumption that cameras are installed near locations with heavy traffic. So this may lead to a biased data set and exaggerates any nearby mobility levels due to a so-called preferential sampling. However, after some research and discussion with domain experts, we later figured out that it was less of a concern in our scenario. So since we only focused on the point of interest along the traffic, and we do not interpolate the traffic density of the lane or areas far from the sampling locations. So a naive interpolation model does not make sense.
Just click on that slide. Switch to Windows.
So yeah, that's how we came up with our new goal with the three major components. The first being a refined data pipeline using vehicle detection. The second being a paired comparison for spatially correlated cameras. And the third is a covariate analysis focused on business and COVID positivity rate. So after all, in order to address all of the three topics, we invented a shiny app that supports an integrated and accessible analysis with an intuitive interface. And then I'll pass over to Ray to talk about our data pipeline.
All right, we'll start with our data pipeline. And before I talk about anything, I would like to state that we're also using Cedar Academy as an example, just as the biodiversity. You can probably see some familiar language. Okay. So camera snapshots are taken at each traffic camera installation, and those are all public available camera images. And then information are extracted from the camera image, such as the number of vehicles in each image, and specifically we use computer vision method, some object detection algorithm to extract those information. The algorithm locates different types of vehicles, and we basically translate that location on boxes into the count of different types of vehicles. And our project focuses on the following parts, starting from the camera data and the vehicle detection we just mentioned. We also did camera comparison analysis between spatially correlated cameras, and we also present several use case studies. For example, correlation of the mobility level with business sites and traffic versus COVID positivity rate. Let's first take a look at our data set. So our main data set for the image is an hourly raw JPEG image from December 1st to December 31st in 2020 of 2 locations, which makes 2 cameras. And we also have historical traffic count data that is hourly for December 2020, but it's among all camera stations. And each record consists of extraction of different vehicle counts from car, trucks, bus, bicycle, motorcycle, and person. Person is not a vehicle, but we do care about people. Some important figures of our count data set. We have 341 camera stations. That's all the public available cameras installed in the city of Zurich. They're installed at different road types. They're installed at intersections, residential roads, and also highways. And if you look at the distribution of all our vehicle counts, you see that 88.6% of them are cars. That's a major reason that in our later analysis, a lot of times you'll see us using car count as the sole representative of vehicle level. And 41.8% of our records show absolutely no traffic, which means they don't capture anything, no vehicle, no people, to mention like a very silent road. So that means our data set is actually quite sparse. And brief look at our technical stack. So we start from the server that is provided by our sponsor, and we have the camera images and the vehicle counts. The translation is done within the server, and this will provide a refined API endpoint for our visualization app to fetch image and historical data. And we supply our app with external data, including bike routes, business sites, services, and etc. So the user could use our interface to do their own analysis. So let's dive deeper into our pipeline, and let's start with the vehicle detection. The first thing I want to talk about is our choice of algorithm. So there are plenty of good object detection algorithms out there, and we ended up choosing YOLO version 4. So YOLO stands for not you only live once, but you only love once. It is the state-of-the-art object detection algorithm when we were doing the project. So an interesting thing you can see from this plot is actually right next to YOLO v4, you can see a cluster of seemingly more advanced object detection algorithms that having like a higher box average precision. And the interesting thing is, if you look at the date they are published, they're actually mostly very recent research done in earlier half of the year. So this is just an interesting takeaway that to see how fast our object detection algorithm, the state of the art, is evolving. And in the future, we will potentially see if any of those methods perform better on our data set. So here we present you with example of our improved detection accuracy. On the left is the output from the old pipeline, where we're using YOLO v3, and it is a method, it's pre-trained model from the open source computer vision library. And on the right is an output from the Duck and YOLO v4, same pre-trained level, pre-trained on the same data set, which is Microsoft Cocoa. It's basically like a huge image data set with like maybe around categories of labels. And you can see that on the right, it detects many more cars. Actually, also with a higher confidence compared to the image on the left. So naturally, the first thing we want to do is we want to get a sense of how accurate detection are before we use those data. That leads us to the inevitable, most nasty part of every data science project, which is manual data entry. What we did is we spent some time and effort manually labeled 720 images on one camera for 24 hours in May 2021. That's an example of the image we're labeling. And we labeled them for vehicle counts and also the state of traffic defined by Q or rear flow. So Q is defined as when there are cars, actually more than 3 cars are waiting at the intersection, and where rear flow is basically when the car are rear flow. So one thing to note that we labeled them for vehicle counts, but not annotations. What that means is for human annotated image, that is available, that is a good thing, data for machine learning training, is actually you have to label the bounding boxes with different categories of vehicles. But because we are just training by manpower and time, so we only label basically the count of vehicles on image. So one question we might as well ask is, how difficult is the annotation task turn out? Why do we care about this? First, it quantifies the reliability of our quote-unquote front shoes, which is our detected, our label count. And also it gives a cost-benefit estimation for future human annotation tasks in case we want to, do large-scale annotation in order to refine or train this specific computer vision model. And the metric we use to quantify this difficulty as well as reliability is a metric called Cohen's kappa score. And on the right is an empirical correspondence between kappa score and label accuracy. So it turns out that for our car counts, we have around 0.62 for the score, and that maps to around 0.8 of label accuracy, which is quite high. And for Q empirical state, it maps to around 0.5 or 6. But it is relatively low, and it suggests that the traffic state of Q inferior flow is actually very subjective. So if we put the data together of detection and our code quote-unquote bunches. You see, for the dark blue lines, they are the labeled car count, so our bunches. The light blue line are the detected car count from our algorithm. And there are two important insights that we can take away from this comparison. First, our algorithm is always undercounting, which means it does not hallucinate. It does not invent cars when there are no cars. And also, our bias is more significant during the rush hours. So you can see compare this part and this part. This is during nighttime where like 3 a.m. You can imagine there's basically no cars on the road. And during rush hours, for example, morning rush hours or the afternoon rush hours, you can see a much more significant bias. So that shed light on the underlying issue, which is the undercounting in our vehicle detection algorithm. So when cars lines up at the intersection, there is semantic feature interweave, and that sort of interfere with the algorithm to detect the right object. So also like one feature of this sort of traffic camera image, you can imagine there being low resolution and you have like very high occlusion of different objects in the scene. That's just a hardware constraint. That leads to two consequences. First, saturation. When I say saturation, I mean if you look at any of this image and their detected car counts in the CSV file, you can see they're capped around 15 cars. Well, you can just casually look at the data set of the actual images and you can easily find a lot of images that is beyond 20 car counts. And the other issue is inconsistency. So what that means is if you look at consecutive images taken at the same intersection, they can suggest very different traffic states. For example, in the first image, you might see 20 cars that is lining up at the intersection. And the second image was like a clearing of the queue when the traffic signal changed. So in that case, the detection algorithms are able to detect more cars because the semantic features are more apart from each other. So that introduced some inconsistent change fluctuations in our data that actually introduced bias in later analysis. The other thing is during nighttime, the vehicle detection algorithm also failed due to headlight, glares, overexposure. That's actually, even as a human, we will have difficulty counting the cars back here that is covered by loss of light. And so in order to mitigate this issue, we propose a post-detection correction model. And one might ask, why don't we just retrain or fine-tune this object detection model? This seems to be the more sensible, general, elegant approach. The problem is we don't have enough human annotation. Simply, we're constrained by manpower and time. And the other thing is very important. Our goal of project is not to get accurate detection, improve the state of the art of this domain specific object detection problem, but we just want to capture the general numerical trend of the mobility level in order to do statistical analysis. So one limitation of our model is actually it's trained with only one camera, although we chose it as general as a single camera can be, it is an intersection road, and we do have a variety of car counts of that intersection. So we had two assumptions, which is the bias in car count depends on the traffic density levels defined by the detected car counts. And it also depends on the state of traffic defined by queue or vehicle definitions mentioned before. And if you look at the pair plot here, you can actually see the distribution between the two states. So when it's at Q, the ground truth seems to be deviating from the detected car counts and it appears to be noisier. So the model proposed for our correction is that we check whether there is a queue or free flow, and then if it's a queue, then we apply the corrected car count using the fitted ordinary sort model, and otherwise we just use the detected car count because it seems to be not suffering from this undercounting bias that much. So just some brief results from our model. The details, the diagnosis are we included in the appendix. If anyone is interested, we can take a look at it afterwards. So it turns out that the Q and free flow categorical variable we included as an interaction term turns out to be a significant predictor. And the root mean square error of our model turns out to be 1.5. And our data scale is around 15 to 20, so that's fair, not great, but fair. And the thing we did afterwards is we include this model as a single table counter for undercount in our visualization app. So other than the user could see the line plot of the traffic they can also toggle this on to see accounting after correction. Another key insight we get from examining the traffic image is that individual camera perspective actually matters a lot. When I say perspective, I mean height, angle, the direction they're facing, and at their installation locations. And also there are different road types. You can imagine for example, if we just compare maybe this road and this road, you see that the same number of vehicles actually suggests very different mobility level for those two roads. If you detect 10 cars at this image, it's probably like a regular state of that intersection. But if you detect 10 cars on this image or that image, then it's almost saturated. It's like the road has been really, really busy. Because everything you can see is like filled with cars. And so this lack of metadata of the camera actually induced bias in later analysis. And I'll hand it over to Nancy to take a closer look at this. Before that, I just want to say the most important takeaway from the vehicle detection pipeline, which is, I guess, the bottleneck or the biggest challenge in every single data science project, that is the data. So one thing is that we're lacking of the human annotation data that can actually refine our object detection algorithm, the model. The other thing is we're lacking also the pre-collected data of camera metadata. It's just we try to find it, and we wish to include it if I think we have people from City of Surrey here. So if they actually have that data, we would very much appreciate we can get it somewhere. But yeah, that being said, I'm going to hand it over to Nancy.
Thanks, Ray. So I'll then take over to talk about comparing camera to camera. So even though preferential sampling, as previously mentioned, is no longer a problem in our case, we still aim to extract useful insights, leveraging the camera's spatial information. So that's how we decided to transition from detecting any bias in camera locations to comparing spatially correlated cameras. Specifically referring to the cameras installed at the same intersections as well as the nearest neighbor intersections. As for the data we used, we sampled 10 point of interest intersections with at least 2 cameras installed, and for the same intersection cameras. And for the nearest neighbor cameras, we used the STNN method from the NGO package to find the corresponding nearest neighbors of the 10 intersections. And also to examine any temporal pattern, we use the filtered hourly data from the AM, which is 7 to 10, and the PM, 4 to 7 rush hours over the whole December 2020. And then we conducted a 2-sided paired t-test for the same intersection cameras and a 2-sample t-test for the nearest neighbor cameras, with the null hypothesis being that there's no significant differences between the car count of the 2 cameras. And we are only comparing the car count since it's the majority of our vehicle counts. And as for the overall preliminary results, as you can see, so for the same intersection, cameras have shown a smaller difference in car count between cameras than the nearest neighbor cameras. And also there's a temporal pattern found, being that PM rush hours have shown more significant differences compared to AM rush hours. Even though, as for nearest neighbor cameras, both AM and PM have shown like significant differences between the cameras. And that was a more general result. And we are also interested in doing a more in-depth comparison for individual camera pairs. So here comes with our app feature, which supports an in-map car count comparison and analysis for the source of differences in the following perspectives: the temporal, camera metadata, and hotspot areas. And there are 2 major use cases, one being the ideal case, and the other is a more common but not so ideal case. which is meaning that the two cameras are vulnerable to the interplay of other covariates, and here is mainly due to the camera metadata. And now let's dive into a real case study, which is the same intersection cameras facing opposite directions to see how this works. So we chose the 56th Avenue and King George Boulevard and targeted at the same intersection cameras 103 and 104, with 103 facing north and 104 facing south. This is an important intersection capturing highway traffic for commutes, and thus a hotspot for analyzing the traffic pattern during the rush hours. Same as before, we did a paired t-test for the two cameras for both of the AM and PM rush hours. And as you may notice, the 103 has captured more car count than 104. And time-wise, there's also a greater differences found during the PM rush hours. And also can also see it from the t-test results in this table. Yeah, so based on the two key observations, we could also do a source of difference analysis. So first, 103 captures more car count. And one apparent reason for that is that camera perspectives are drastically different. And one may also notice from the real-time image that this is also a one-way traffic lane from north to south. So 103 would typically capture queues and 104 would capture flows. So that's why 103 would capture more car count in general. And also the second, more significant differences were found in the PM rush hours. So this could be explained by there are more people traveling back home from workplace during the PM rush hours. And we also have some caveats and while we worked on the analysis. So we're lacking accurate and reliable data for camera metadata. And if we have this data, we could potentially incorporate it as a categorical covariate in our comparison analysis. And also it would help with the traffic flow modeling in the vehicle detection stage. Another feature we developed is a weekdays only toggle. So people may wonder if there would be a more consistent rush hour pattern during the weekdays. So if there's any increase in the difference between cameras during weekdays. And here, since we're only filtering on the weekdays only data, we have a smaller sample size. So we used the coherence score here to conduct the comparison between cameras, which is standardized, which is similar to t-test, but it's a standardized, so it doesn't subject to any sample size changes. And as for the results, we have seen a slight increase in both of the d-values for both of AM and PM rush hours, and there's also noticeably very large difference during the PM rush hours for the weekdays only data. And one can also say that there's a slight more consistent rush hour pattern during the weekdays. And that concludes the case study for the camera comparison. I'll hand over to Martin to talk about the covariate analysis.
Okay, so for the next few slides, we're going to talk about how someone can implement raw traffic into various applications of interest. So you may already know that the COVID-19 pandemic has caused a lot of economic disruption among small businesses in Surrey. and beyond. One thing we realized is that we can actually use the traffic counts found in the cameras to analyze the change in traffic over time, to analyze business patterns in Surrey. And we also realized that we can also investigate the relationship between COVID-19 positivity rates and traffic behavior. Okay, so I'll walk you through it in a miniature case study. First, we're going to emphasize on the restaurants near Highway 1 with these cameras selected. And the analysis that we're going to do is we're going to walk through an analysis of aggregation of car counts during AM, PM hours. We're also going to walk through traffic activity for peak hours, and we're also going to discuss potential uses in cases if we have more data. Okay, so what you're seeing here on to your right is the average car count for all three intersections in the rush hours, AM on top, PM on the bottom for the entire month of December. As you can see, as you can expect, that there's more traffic counts in the early morning rush hour as well as the late evening rush hour. The y-axis shows the magnitude of the counts. Overall, this actually provides an interpretation of the performance of businesses of nearby business and economic activity. Okay, so this is the slide which is kind of similar to the previous slide. However, we're just going to focus on the individual cameras in each intersection. As you can see, there's more counts in the intersection at 152 and 104, and less at 152 and 105, which is labeled in blue. But in conclusion, that we conclude that this area is most likely to be a hotspot for high traffic activity, and therefore businesses around these areas are more likely to see gains in potential marketing opportunities and whatnot. So before I move on to the next slide, it's not seeing the map here, but just a little bit north of it is highway number 1, which is a major route for exit and entrance routes for people working in Surrey and beyond. And you might ask, okay, well, since 152 and 105 is a little bit more north of Highway 1 than 152 and 104, you expect that there's more counts for 105 than 104. However, this is not the case shown. And this, in the next slide, we'll discuss why. This ultimately doubles down on the emphasis on camera perspective. So the reason why the blue intersection 105 is not picking up as much counts as it's supposed to, it's because it's facing west to a recreation center, while 152 and 104 is the camera is facing south, which means you're picking up cars facing north, and those cars may or may not be potentially going on highway 1, whatnot. And for green intersection, it is like a detour to highway 1, so it kind of makes sense why the graph you saw the last slide behaves the way it should be, with 152 and 104 being the highest car counts, and 152 and 105 being the most least. So potential applications of analysis. So these 4 industries are, you can actually use these 4 industries as a way to analyze traffic data and apply it to various sectors. It's important to note that all 4 of them can be related to each other. So for example, like if you're an analyst working at a census bureau, right, you would want to find how many people live in Surrey that go to work, or how many people that live out of Surrey that go to work. So that may be beneficial that knowledge be beneficial to potential investors who are looking towards establishing small business in Surrey, and actually relating to business itself, they can actually take this information and find when to increase marketing and when to employ staff members to meet customer demands, especially in rush hour times, because a lot of people are turning on the radio when they're driving and whatnot. And we like to emphasize that all analysis can be conducted with like pre and post-COVID data. So like if we had more data, we can actually find like the actual change in the business activity more clearly. So the next case study that I'll walk you through is the trends in COVID data with relation to the traffic data in relation to COVID positivity rates. So our question for this case study is that we asked, does the number of car counts seen in the traffic rates affect the number of COVID cases in the future? And one of the tests that we use is a granular causality test, which is useful because it's useful for forecasting observations in the near future, and it's useful for 2 or more time series data. And if we're able to forecast positivity rates, then we're able to forecast future lockdowns, which may indirectly forecast potential like disruption in economic activity and whatnot. Okay, so we conclude that it's actually possible to use car counts to predict COVID positivity rates. However, in certain days of time, so if you can see here, the p-values are like less than 0.05, so like around 7 to maybe like 13. That's a great time to predict the COVID positivity rates 7 to 13 days from today, present day. Interesting enough, if we actually switch the formulas around, so like if we said, okay, does COVID positivity rates predict traffic counts, then we actually see an insignificant amount of relationship. So that's interesting to see. So, but in conclusion, we are able to determine that the car count is able to predict the increased amounts of COVID positivity rates in certain days from now. However, if we switch the formulas around, it has little really effect, and we can't really predict much due to insignificant p-values. So we're going to move on to app demo next. Just a highlight of overview of the app demo. There's 2 parts to it. There's one's the visualization part and one's the statistical analysis. For the visualization part, we have a lot of overlays to assist the analysts in finding clues in data. For example, like we have business overlays with bike lanes. We also have a heat map mode to analyze the changing traffic in time. We also have statistical analysis, which helps the analysts focus on specific time periods so they can see like what's going on in traffic. We also have same intersection input analysis, as well as nearby cams used to visualize the data near businesses. And now we're going to just transition over to the app. Oh, you're not in Zoom? Okay.
Where should I?
Sorry. So just a little bit more time because we forgot to join this computer to Zoom. DSSG. Like the trend. Sorry, technical difficulty. Have the UI problem, but
Yeah, it's working. All right, so this is just a quick tour of like our app. So over here you see the map of Surrey. Can you see? Yeah, over here is the city of Surrey. Here, you can this is the base map mode, and there's an option to switch to heat map. But first, let's talk about the overlays on the base map, which also known as the CAM map. So over here you have the overlays from stores to services. So if you zoom in, there's a lot of information, including like the title, the name of the store, and as well as like the nearby cameras around. In fact, if you actually click two or more cameras, and then go on nearby cams, and you select the businesses, it will tell you, okay, well, which cameras is a business around. You can also adjust the radius from like small to big, and then furthermore, you can
also see the visualization.
Yeah. Furthermore, you can also see the visualization of the cameras and like the moving average. There's also bike routes that you can see from the range from all different types of bike routes, from bike lanes to share traffic. We also have boundaries. So the default selected is Surrey, but if one wants to get more detail and look at a specific neighborhood, let's say Guildford, it shifts to the neighborhood over here, highlighted in the gray. There's also a feature, a heat map feature, where you can observe the change in traffic over time. like that. It's useful if someone wants to see like a certain area change in traffic in certain area within a given time period. Next, I will move. Oh, so you can zoom in. Sorry, yeah, you can zoom in and see. You can zoom in and see like how different intersections behaves and whatnot. Next, I will move on to Nancy's part, and she'll be discussing about the analysis.
Yeah, thanks, Martin. So I'll take over to introduce more about some of the core visualizations we have on this space map. So first of all, as you can see, we have this traffic explorer, and that is our core visualization tool for the vehicle count for the selected cameras. And here we are selecting on these 4 cameras, for example. Can deselect. And now let's focus on these 2, the 103 and 104 as an example. So the user will be able to adjust the date range and time range to see like a specific pattern over time. Say I want to filter on the first week of the December, and we can also see a trend. You can also see like the car count changing over time. If you're interested in the AM and PM rush hours, you can do this quick actions, and we can also filter on different vehicle count here. And now back to the panel, we also have the same intersection and nearest neighbor comparison table, which demonstrates the t-test results for the 2 cameras for the AM and PM rush hours. And also there's like a requirement for the 2 cameras to be either the nearest neighbor or the same intersection cameras. And for example, these 2 cameras, have shown like significant differences during this time range. And also, last but not least, we have this correct for undercount feature toggle, and that is using our post-detection prediction model introduced by Ray, and that shows like the corrected car count for the selected cameras. And that concludes our app demo. I'll hand over to Martin. Back to the slides to talk about the implications.
Okay, so one of the implications that this data we can use raw data is that it's very diverse. And it's very flexible to use it in various industries. But sticking to the DSSG's theme of social good, we can use this data. Non-profit organizations can use this data via providing aid to underrepresented areas by analyzing traffic patterns. So if traffic cameras picking up low to no cameras, or like one area is like really crowded, if one area is having a high traffic activity and like another area is having low traffic activity, that's a good sign of that the area that has low traffic activity may benefit from some sort of aid or whatnot due to probably the fact that that area over there may be underrepresented. And we also have governments, as they can provide insight on where to construct essential services and based on traffic patterns. And we also have small businesses like we discussed before, and we also have neighborhoods. So cameras that areas that have less traffic cameras may be prone to have an increased amount of crime. So neighborhoods can promote like neighborhood watch programs to help them combat that. And I'll take this, give Ray the final conclusions.
Yeah, so in the end of our presentation, we just want to reiterate what we learned from this project and also some future directions we think might be taken. So first, we investigated the whole pipeline from camera snapshots to the data extracting and constructed data set, and we have investigated both its potentials and limitations. So the most important thing we learned is data is crucial, but also what kind of data is crucial. For example, human annotation data used to retrain and refine our object detection model. And camera metadata, as we can see in our use case studies, it can be used to rectify our analysis. And also, of course, we're using Zero here as an example, but if we can get more data, we can generate the results in more cities around the world and test our beliefs. There's also one thing we recognize is the importance of accessibility to various kinds of data. That is also what our app is trying to achieve. So it's the access to various kinds of data not only limited to numerical traffic count, but also the camera images that help us to make sense out of this experience in our use case. And one future direction is also related to the previous data we mentioned is to model the traffic flow, like actually model of the traffic flow with an annotated region of interest, so we can rule out the car, for example, parked behind the thing. And we can also take into account the camera metadata, for example, the direction, which is important in the traffic modeling problem, and also the traffic state of queue and free flow. So that concludes our presentation, and we would like to thank everyone in person or virtually for listening to this presentation, and we would also like to thank everyone that helped in this project. So are there any questions?
I just have two short questions. So
Yeah,
first
sure.
one is, have you started seeing cars after analyzing so many data in your dreams? Yeah, the second one, I was wondering the definition. So the way you define the free flow and queue, right? Is it a standard practice of defining the flow? Because I would expect it to be per unit area and to standardize the number of cars per amount of road area, basically. Maybe it's a bit better metric.
We didn't really, if you're talking about the queue and free flow, it's actually a categorical variable that is just saying whether this intersection is like basically at red light and at the same time the car parking, queuing up, waiting to pass. So it's not really like the flow in sense of traffic modeling flow.
Okay.
I actually didn't like. Can you reiterate the first question?
No, I just asking whether you start seeing cars in your dreams after analyzing so many images.
It's actually found that yesterday, the day before yesterday, we were going to the Earth Science building for practice, and there was like a little vehicle sign outside the Earth Science building. And I was looking at it, I was like, that's nice vector graphics we should include in our slide. Any other questions?
I have one thing. Actually, I don't have any question. I'd rather have a comment. That's okay with you, Raymond?
Oh, sure.
So, I'm from the Cedar Academy Society. We are the industry sponsor. Okay, stand up. We got to give it there. No, I can stand here. It's okay. So we are the industry sponsor of this program. And in the last three months, so we've been working with three wonderful individuals. And obviously from DSSG, Raymond, Kevin, and all the others. It's been great experience, and it's definitely a journey for sure, but it's definitely a great experience for us. There's not enough good things I can say about the three fellows here. Their work as a team, that's really great. Okay, I actually think that's the number one achievement you have here. They work as a team, they It shows great amount of skill, technical skill. You can see that already, right? The presentation skills, everything. And last definitely is that shows the commitment to work. That's really important. Sometimes I feel so tired, just want to drop the whole thing in the middle of the semester, right? But they didn't. They pulled through, and they did it. And I want you, this is not the moment, but I want you to take a moment to feel proud for your own achievement. This is quite something. And I would like to thank you so much for all the work and definitely for the coordination by DSI. The stuff they did, well, I don't have to stress on the technical part. You guys are technical experts. We are not. The stuff they did, I guess from my point of view, is that has really expanded our view of the raw data we have collected. Historically, we have stakeholders and clients, per se, who are more interested in extracting number, the CSV files, right? They were not interested in original, they were not interested in the raw images. But through this cooperation with DSI, I think we can take another view of the raw data we have now. And it's going to greatly expand our client base and our stakeholder range. So for that, I also want to thank you very much. It's really helpful. I know that maybe starting next month, all three of you are going to take separate methods. Like separate paths with a future career, maybe you go to school, maybe you go somewhere else. But take a moment, enjoy this moment. You have achieved a lot. I really want to give you confirmation in that direction. And that's all I have to say. Now, we have a couple of participants from my side, Corey and Williams and Karen. I don't know if they have questions. Oh, they have sign off. Okay.
We have a question from Yulia. Julia.
Hey.
Julia.
Hi. I don't know if you can see me. I just thought it was really, hi Raymond. It was really interesting your case study on COVID cases and the traffic counts, because actually where I'm currently living, they are using the same data to put restrictions. So they actually are trying to control COVID spread by limiting the license plates that can go out on certain dates. So I just thought it was really interesting because apparently there is a correlation, as you said, and it's been pretty effective to like curb COVID cases where I'm from. So that was really cool.
I actually have a question on that, if you don't mind. Come closer and speak up. Sorry, I have a question, if you don't mind. What formula did you use? Like, did you use kind of the same formula that we did, or?
Oh, I'm not sure, because that's like the government. I'm from Costa Rica, so I recently watched a press conference because they basically are using license plates as a way to control restrictions so that they can curb COVID spread. So for example, on like Mondays, only if your license plate ends on 1 or 2, you can go out. And actually their reasoning is that there's a link. They found a similar link to what you found, that, traffic counts can actually like predict COVID rates a few days after. So yeah.
Can I add something to that? So, sorry. So when you're talking about license plate, I just realized I might as well add that to it. So like the cameras things we are using, it's a public database, so it means everyone can just go online and get those camera images. So that introduced actually privacy issues. And the thing we confirmed is that you can't really see any license plate or people faces from the images. They're by intention blurred, shrinked in resolution, so no one can actually recognize any license plate. But if like any government had access to that, then yeah, I mean it could probably help in the restriction policy you're trying to make there.
Okay, thank you, Julia. Last call for a question before we break at 12. All right, so if there's no more questions, please join me in thanking the team. We'll be taking lunch, and Zoom will be restarting at 1.